Hey all, it's Mrs. Blasky. Today we're going to be talking about topic 5.3, which talks about other ways to determine the order of a reaction. Remember that order tells us about how that rate of the reaction, the speed of the reaction responds to changes in concentration. So zero order means we can change the concentration and not cause any change in the reaction rate. First order means that we do cause a change in the reaction rate that is proportional to the change in concentration. And second order means that our change in reaction rate is exponentially related to the change in our concentration. So today we're only going to be talking about what we call elementary reactions or single step reactions, meaning that there's usually just one reactant changing. There's nothing multiple reactions going. Previously, we saw sometimes you could have two reactants and one was second order and one was first order. This one, we're just dealing with one single order for the entire reaction. A zero order reaction, like we said, the rate does not depend on the concentration of the reactant, which means that if we graph out the concentration versus time, that slope of that line, how the concentration changes with time, is going to be constant. The rate, which would be the slope, is not going to be changing at all depending on how the initial concentration of that reactant is. So for a zero order reaction, we can graph this concentration versus time, get a negative straight line slope. And that slope is actually our K value, our rate constant. So we can write out an equation. This is called the integrated rate law for a zero order reaction. So this equation is on your equation sheet where we have the concentration at any time is equal to the initial concentration of that reactant minus KT. K is the rate constant and T is the time at which we are measuring this. So this is written in slope-intercept form. For first order reaction, the graph is a little bit different. In order to get a straight line, we cannot graph concentration versus time. That rate is changing as time goes on because the concentration controls how fast that reaction can go. So for a first order reaction, if we graph concentration versus time, we actually get a curved negative slope graph. In order to get that into being a straight line, we need to graph the natural log of concentration versus time. Why natural log? Unimportant at this time. We just need to know that natural log makes it straight. So again, the slope of that line gives me my rate constant, gives me my K value. The equation for that line is the natural log of the concentration at any time minus the natural log of the concentration at the beginning. That little zero means at time zero equals negative KT. Again, this equation is also on your equation sheet. There are two different ways to sort of write this equation out. The subtraction version is the one that's on your equation sheet, but because of the way natural logs work, we can also take the natural log of the concentration at any time over the initial concentration and simplify that down into one term. Second order reactions also have a curved line for concentration versus time because that concentration is changing or the rate is changing exponentially with the concentration. In order to get that to be a straight line, we need to graph 1 over concentration versus time. That gives us our straight line. The second order graph is the only one that has a positive slope to it. So that slope is equal to K. Again, the equation for this one is also on your equation sheet. Second order integrated rate law is what it's called. It's 1 over the concentration at any time minus 1 over the initial concentration equals positive KT. All those other ones said negative KT in there because they had that negative facing slope. Being able to identify what order reaction you have based on the graphs is a very, very common thing to show up on the AP test, both in the multiple choice questions and in the free response questions. So we'll be practicing that a lot. Got a fantastic little summary of all of the different information we have about zero, first, and second order reactions here, along with their integrated rate laws, where they get straight lines, and also the units of K for each of those orders of the reaction. You can memorize those, or as long as you know how to calculate it, that's really the most important thing. One special thing that we can talk about for first order reactions is called half-life. We're only going to be required to know this for a first order reaction. You can do half-lives for zero and second order reactions, but AP only really wants you to be able to do it for first order. So the half-life is a different way of measuring the rate of a reaction. Half-life is exactly what it sounds like. It is the time it takes for a reaction to go through half of its reactant. So for the concentration of the reactant to decrease to 1/2 of its initial value. The faster the half-life is, or the shorter the half-life is, the less time it takes, the faster the reaction is. So every time a half-life occurs, we go through half of our concentration. So we can see that if we start with a concentration of 1, when one half-life has gone by, we're down to a concentration of 0.5. If a second half-life amount of time passes, then we're down to half of that, which is 0.25. Another half-life occurs, we're down to half of 0.25, which is 0.125, et cetera, et cetera, et cetera. We especially talk about half-lives when we're talking about radioactive decay. Because we care about half-lives, we want to know how long that sample is going to be radioactive or measurably radioactive. And so we see that a lot for radioactive substances. A couple different things that can get figured out for half-lives. We do have a special equation for the half-life of a first order reaction. It is independent of the initial concentration. This equation comes from that natural log calculation of saying if we initially have 100% and then at time t we have 50%, how much of that chemical would we have left? And so we can figure that out with this. As long as we know the K value for that reaction, now remember K is reaction and temperature dependent, we can figure out how much time it takes for half of that reaction to occur, or vice versa. If we know the half-life, we can figure out K. So we are going to see some questions that talk about how many times this has happened. We can either calculate it this way, or honestly, we can just take that initial concentration we have and divide it in half multiple times to figure out how much we've got left after a certain number of half-lives. Or we can also use this idea of percentages and those integrated rate law equations to say, well, if initially I have 100% at time 110 seconds, I only have, well, if it's 73% complete, that means I would only have 27% left. I can use that integrated rate law equation to find my rate constant, to find out how much time it takes for that to happen, et cetera, whatever the question is asking for. So this is going to get into some decent amount of math. We're going to have to be using our calculator a lot. We're going to have to get super familiar with our natural log button on our calculator to see how all this is going to work. So again, we'll be working on this in class a lot. If you've got questions, let me know, and I will talk to you later.